Welcome everyone. In this talk, we will sense the pulse of a data stream like Twitter posts, credit card transactions, or Internet of Things sensor readings in three ways. First, we will cover the DGIM algorithm, which is a clever bit-based strategy for approximating the count of ones in a sliding window. Second, we will see how to compute moments from data streams. We will learn how to estimate statistical moments like mean, variance, and skewness using compact sketches. So we do all these without storing the entire dataset in one pass and with limited memory. And last but not the least, we will discuss how to identify trending items with exponential decay. We'll discover how exponential decaying windows help surface emerging trends by giving more weight to recent data. So this is a crucial method for dynamic environments like social media or sensor networks. So this is very unlike the traditional data landscape. Traditional databases expect finite data, so you can pause and analyze, but streams never pause. Streams are continuously coming in. So we need smart, lightweight methods that estimate things on the fly without storing everything. So sensing the pulse is a beautiful metaphor. We want to monitor a living, beating data stream in real time while detecting trends and abnormalities as they happen. So the rest of the talk will show clever algorithms that trade a little accuracy for enormous gains in speed and memory. So let us dive in. So a good introduction to the concepts of data streams, sketches, and counting is provided in this talk that I gave a couple of months ago. You can check if you are interested. But you should be able to fairly follow through today's talk, even if you did not watch it. I'll cover some basics. So this is the video. Anyway, I'll not play it. You can watch it. You can search. I have a YouTube channel, and you can search there. Okay, so the first algorithm is about counting from streams. Suppose data comes continuously, and we want to know how many distinct things have we seen. For instance, unique users visiting a site. So this is a stream, so we can't store all users. It's too expensive. So there is an algorithm called Flajolet-Martin algorithm, which I discussed in the video that I showed previously. It proposes a probabilistic trick. So Flajolet-Martin provides a quick guess for cardinality of a stream using clever tricks. But it is not a precise count. Big data is all about approximations. So big data is essentially an approximate science. What we do is probabilistic counting of distinct elements. So the idea is we hash each element. Each element is like each event. When we say stream, it's a stream of events typically. The event could be a credit card transaction, or it could be a user visiting a site. All those are events, and those streams of events are continuously flowing in. So what we do is we hash each of these events. An event is represented by a tuple, right? You know what a tuple is, right? So it's represented by a tuple, and it's also called element. So we hash each of these tuples and look at the position of the least significant one bit in the binary hash. So we convert, first we hash the event to a table, and then we look at the least significant bit which is set. That is because the probability of getting that bit pattern gives us statistical information about how many unique items we have seen. So that's really ingenious. I mean, nobody would. It's not very apparent, but somebody could see that the least significant bit that is set when a number is converted into its binary equivalent tells you some statistical information. So that is the crux of this algorithm. And of course, we need to average over multiple hash functions because we cannot trust any hash function. So we use multiple hash functions and we average it out. And we surprisingly get accurate estimate of the cardinality using just a few bytes. So this is one of the important milestones in streaming algorithms. It showed that approximation can beat exactness when resources are tight. So I'll spend a few minutes detailing it. So um, let me first explain the intuition, right? So suppose we are for every element that is coming in the stream, we are tossing a set of coins, right? So if the coin if turns heads, the bit is set, and if that coin turns tails, it is set to 0, right? So they are a set of coins. So what this algorithm assumes, and it was proven also, is that the position of the first heads corresponds to how rare that hash outcome is. So the more unique items you see, the higher the chance that one of them will have a long run of trailing zeros. So the largest such run tells you roughly how big your set is. So the algorithm elegantly turns randomness into an estimator of distinct count. So the real magic is that we only need to store the maximum observed zero run length, right? The number of zeros is what we are going to store, not the whole data set. So that's what makes it scale. So that is the intuition, but the algorithm itself is very simple, even much simpler than the intuition. So first is we hash every element in the stream to a number, and we convert that number into a bit string. So this bit string is typically constant, like 128 bits, 256 bits, and so on. So this is straightforward, right? We use a hash function, we convert the tuple into a number, right? So some more details I explained in the previous video, in case you are not familiar about hashing. And so once we convert the event into a bit string, we count the trailing zeros from the start from the ending. So for each hashed element, the number of trailing zeros in the bit string is recorded. And then we have a number of events have come through and we have hashed them. We need to keep track of the maximum number of trailing zeros across all elements R. So that's it. That is the algorithm. Suppose the maximum number of um, trailing, suppose the hash the current hash number is 16, right? 16 is 1 followed by 3 zeros. So what is the maximum number of trailing zeros we have seen so far? It is 3, right? 1 followed by 3 zeros. So we just keep track of that number. And next time when suppose 33 comes, the number of zeros, the trailing zeros will increase to 4, I believe, right? Yeah, 4. because 33 has, I believe, 4 zeros, right? So that is the idea. We just keep track of the maximum number of trailing zeros across all elements. And then the number of distinct elements n is estimated by the formula 2 power r. That's it. So if the current event is hashed to the number 33, then the number of distinct elements we have seen in the stream, number of distinct events or elements we have seen in the stream is 2 power 4, right? So that is what it means. So that is the estimate. It's a very simple and easy algorithm. The proof is a little bit involved, the intuition and the proof. But if you are interested, you can watch the video that I pointed to in the previous slide. Okay, now we want to extend the idea of counting to sliding window. So we shift gears. Instead of counting distinct elements, let's count the ones in the last n bits of a stream. So what is an example of a sliding window of bits? So a typical real world example is the number of fraudulent transactions in the last 1 hour, credit card transactions. But we don't have the memory to store all the n bits. I'll tell you why, how it can scale up. So we don't have the memory to store all the n bits. Now this algorithm called DGIM, so DGIM stands for the inventors of the algorithm, Datar, Gionis, Indik, and Motwani. Rajiv Motwani was a professor in Stanford University, unfortunately passed away. So they invented this algorithm. So the algorithm basically summarizes the past very cleverly. The key idea is to divide the stream into buckets of exponentially increasing sizes. So we have a stream of bits coming in, and we want to group them into buckets. And the sizes of these buckets will grow exponentially, like the first bucket size is 1, the second bucket size is 2, the third bucket size is 4, so on and so forth, exponential, 1, 2, 4, 8, 16, like that. So we only need to maintain a small number of these buckets, each storing how many ones it contains. So that gives us an approximate count with very little memory. So this sliding window concept is essential whenever recency matters. For instance, tracking the last 1,000 tweets, tracking the last 1 week of credit card transactions and things like that. So that is the idea of a window. It's bounded by time. So that is the problem statement. So let's connect the theory to practice. So here are some use cases of approximate counting of ones in binary strings. So the first is in big data processing. So systems like Spark and Hadoop use these approximations to estimate dataset sizes across distributed nodes without moving terabytes around, right? You all know Spark and Hadoop, I hope, right? So these tools do distributed computing with terabytes or even petabytes of data sets. So tools like DJIM are extensively used in these, or algorithms like DJIM are extensively used in these tools. So the next application is web analytics. So to estimate page views or user actions, knowing trends without logging every click. So that is the application. And DNA analysis. So we want to count patterns in genetic data streams to find recurring motifs. So this is critical for real-time bioinformatics. So if you have any question, please post them in the chat window. And social media to track hashtags, engagement, trending topics without storing every post. So this slide reminds us that just because the algorithms are approximate does not mean that they are unimportant. These algorithms power huge parts of modern data infrastructure. So there's a lot of potential here. So I'll probably turn off uh, the alarm bell because sometimes it can get annoying. Okay. So yeah, these are the applications. There are a lot of applications. So let us look at the problem statement in a little more detail. So remember, we are not storing the entire stream. We don't have the memory to store the entire stream, only the counts, which take much less bits. So one example is Amazon wants to know how many iPhones of the latest model were sold in the last 1 month. So, uh, so Amazon has to do something called as the market basket analysis. So if iPhone is in the transaction, then a bit is set. Otherwise, the bit remains zero. So that is how the stream is generated. So every transaction, right? A transaction is like a market basket. Um, so the transaction can include a number of items. And if iPhone is present in the transaction, if one is sent in the stream, otherwise a zero is sent. So suppose the window is 1 month. So we get all these ones and zeros. So the first is a one, that means this transaction had iPhone in the shopping cart. The next one is a zero, that means this shopping cart did not have iPhone, and so on and so forth. So that is the stream that we want to analyze. So the problem with this is that the volume and of course the velocity also. What if there are 10 billion transactions on an average in a month? Right? It is not uncommon for Amazon to have 10 billion transactions, a company like Amazon. So 10 billion bits is 1.25 gigabytes. So it is infeasible to store the entire stream. And we cannot sample and assume proportionality to reduce the count, right? So if you assume proportionality, and if there were n number of bits, what would be the number of iPhones if uh, so you understand the meaning of proportionality, right? So if the car, okay, let me put the expression here. So n is the number of bits in the stream, t is the number of ones in the sample, and s is the number of bits in the sample. Then you can estimate the number of iPhones by using this proportionality, right? If there are n number of bits in the stream and t is the number of ones in the sample and the sample size is s, then n into t by s is going to give you the number of iPhones in the population in the stream. But this is not applicable to us. Why? Because you cannot assume that this stream is uniform in the distribution. There can be ones continuously, there can be spikes in the iPhone sales, or there could be absolutely no sales also. So it's very it's non-uniform. So you cannot assume proportionality. You cannot assume a uniform distribution of the ones and zeros. So you cannot do this. You cannot assume proportionality because stream cannot be assumed to be uniformly distributed. So then the problem is, how can we count the ones in the last n bits by storing just just log squared n bits per stream? So this is the intuition for the DGIM algorithm. It's not the algorithm itself, but just the intuition. So if you remember complexity of algorithms, the complexity is measured across two dimensions. One is the memory and the other is the speed. or the time taken, right? So here we are looking at the complexity in terms of the number of bits, because that also is a challenge for streams, right? So storing n bits is impossible. So we want to store in an order of log squared n bits. So how are we going to do it? So uh, one idea is, what if we exploit the structure? Suppose we break the stream into regions of sizes, exponentially increasing sizes, 1, 2, 4, 8, until n. Now the number of regions is logarithm of n, right? Okay, let us look at it in a little more detail. So binary representation of n will take how many bits? Log n to the base 2 bits, right? So example, suppose n is equal to 16. Binary representation of 16 is 1 followed by 4 zeros. So it takes 4 bits. So if n is equal to 30, binary representation is 5 ones followed by 0. Sorry, 4 ones followed by 0. So 5 bits. So you get the idea, right? So we just need log n bits. If we just store the counts, right? What if we break the stream of bits into regions with exponentially increasing number of bits? So the first bucket has just 1 bit, the second bucket has 2 bits, third bucket has 4 bits, and so on and so forth. So like this, right? So then what happens? And then store the count of the number of ones in each of those regions. So these are the buckets in the stream. The stream could be bucketized into these. And then we store the counts. So the first bucket has 1. So we can allow 2 buckets of the same size, say, for instance. So 2 buckets of size 1, 2 buckets of size 2, and the last bucket is still forming. So there are 10 ones. Or rather, the last bucket is already formed. The length is probably 16. This is 8, so this must be 16. So there are 10 bits in 10 bits which are set in the last bucket. So we just store the counts. So then we'll end up in at most logarithm of n regions with at most logarithm of n bits for each region, right? So the total number of bits that need to be stored is order of log n times log n, right? Is that clear? So the idea is very simple. So break the stream into buckets of exponential sizes, right? And each bucket will hold the um, the logarithm of the number of bits, right? So there are logarithm of n number of buckets, and each bucket has at most logarithm of n to the base 2 number of bits. So you get log squared n. So you can save space that way. But we want to improve further. So we want to uh, even further reduce the storage. So let us formalize that intuition. So we are going to maintain buckets like before, each storing the number of ones and a timestamp for when it started. And just like before, so imagine a stream of bits indicating whether a credit card transaction is fraudulent or genuine. So creating the regions or buckets with size based on the count of ones received. The buckets store the number of ones in them, just like just like before. But the difference is this time the buckets will be based on the count of ones received. So in the previous case, in the intuition case, what we did was we just counted the number of bits irrespective of whether the bit is a 1 or a 0, right? So here we counted 4 bits. Uh, and here we counted 8 bits and so on and so forth. Okay, we are not yet at the size. So I think I take back the number of buckets, the equal buckets is not applicable yet. So in the intuition part, we just divide the stream into buckets of sizes with exponential length. So first bucket is 1, second bucket is 2, third bucket is 4. The size indicates the number of bits in the bucket. The third bucket is 8 and so on and so forth, right? So that is how we divide the bucket, the stream into buckets in the intuition part. In the DGIM algorithm, what we do is instead of forming the buckets based on the number of bits, we form the buckets based on the count of ones that are received in the stream. And then, like before, buckets store the number of ones in them. So I got mixed up a little bit. I thought these are uh, uh, these are the count. I mean, these are anyway the count of the number of ones, but the buckets are based on the number of bits here, not the number of ones in the buckets. So that is the difference in DJIM. The main difference is the size of the buckets is based on the count of ones received. So these buckets keep forming, but we need a way to merge or break the buckets and maintain the exponentially increasing sizes property, right? So the bucket sizes double as we move backwards in time. So 1, 2, 4, 8, and so on and so forth. So we ensure that the bucket size in terms of number of ones is exponentially increasing. So when too many buckets of the same size appear, we have to merge them, right, into one large bucket. So that way we want to keep the memory bounded. We want to reduce the memory used. So as the new bits arrive, okay, that is the next part. So as the new bits arrive, one or more of the old bits need to be discarded because remember this is a sliding window. We want to deal with only n bits, right? So as the new bits arrive, old ones expire, and we always keep track of just the last 10 bits. So the elegance here is the self-adjusting nature of the buckets. So there is no manual resets needed. So this is the DJIM algorithm. And so we need to allow some leeway, right? When forming buckets and breaking the buckets, we cannot work with just one bucket, right? So what we do is we allow 2 buckets of the same size. We can allow more than 2 buckets also, but there's a problem. What is the problem? The problem is again memory. Each bucket takes memory. If you have more number of buckets to be combined, then we need more memory to store the information about the buckets. Okay, let us take an example and see. So this is the stream of bits, ones and zeros, right? So we can have buckets of the 2 buckets of the same size. So here 2 buckets are of the size 1, and here there is just 1 bucket of size 2. Again, 2 buckets of size 4, and 1 bucket of size 8, and so on and so forth. So what are some of the observations that you make? So Uh, Obviously, there will be some error because these algorithms are approximate. So the rule of thumb in most of these big data algorithms is simplicity with controlled error. And uh, and we want to reduce the number of buckets. So that's the other thing, because more number of buckets means more memory. Uh, and the other thing to note is that we don't allow more than two buckets, right, of the same size. Um, because allowing a tiny overlap reduces storage while keeping the estimation error small, right? Remember, the error is all in the last bucket. Why is the error in the last bucket? So the buckets are forming from right to left. So the last bucket on the left is sometimes incomplete. Why is it incomplete? Because we save only the n number of bits. If the time lapse is more than n, we drop the bits in the bucket. And so that's the reason why this bucket is incomplete sometimes, right? So basically, uh, we want to obtain bounded redundancy for stability. This is common across all streaming algorithms, right? So the estimated count of this kind of an arrangement is given by this term, right? So on this slide, BK is the bucket to the left, right? BK is the bucket to the left, and bits are flowing right to left. So the buckets are forming from right to left. So a bucket can be thought of as a record. What does a record comprise? It comprises two things. One is the timestamp of its end. So this timestamp at the end. And then the second thing is the number of ones between its beginning and the end. So the timestamp can be saved in how many bits? If there are n bits, the timestamp can be saved in logarithm of n number of bits, right? So we need an order of logarithm of n bits to store the timestamp. And to store the number of ones between its beginning and end, we need logarithm of n, right? Remember the discussion we had previously, the binary, I think this slide, right? So this discussion. So we will need logarithm of n to store the number of bits in each of these buckets. Where is that? Yeah. So that is the idea. So the summary is that we don't need too much of memory to store these bits. And the other observation that you should make is that buckets form whenever a 1 appears. If there is a 0, that is skipped. We don't care for zeros. We form the bucket only when 1 appears, right? So how did we improve our intuition? So the intuition is improved by forming the buckets based on the number of ones instead of the number of bits. So that's a lot of savings. And the other idea is to ignore the zeros. If there is a zero, we just ignore them and start the bucket only when there is a one that appears. So that way we can discard a lot of bits, right? So two improvements will make a lot of difference, right, in the number of bits stored. So the idea is to count the number of ones in all these buckets. The first term is the sum of all the ones in all these buckets. And the last term is half of the last number of ones in the last bucket. Why do we take half? We'll talk about it a little later. And because this is the source of error, the bucket is still forming, right? So that's the reason why uh, we divided by 2. Why 2, we'll come to that in a little while. But for now, just hold on to that thought. And the other thing is when 3 buckets, so now there are 2 buckets, right? Of size 1. Suppose there is another bucket. Suppose there is another one which comes in. So there will be 3 buckets of size 1. So what do we do? So when 3 buckets of equal size appear, merge the oldest 2. That means we are going to merge these 2 and let the 1 be here. So you never have more than 2 of any size, right? At any point of time, there cannot be more than 2 buckets of any size. So this slide brings the algorithm to life pretty much. So overlapping rectangle, or rather the rectangles that age as the stream progresses. So even without exact math, the visualization makes the pattern of exponential compression intuitive, right? Hopefully, right? You would have made out the algorithm from the slide itself. So, so the buckets need to follow some housekeeping rules. So there are 6 rules. First is the right end of the bucket is always a position with a 1. Why? Why is that so? Because we want to ignore zeros. We don't want to save the zeros. We don't want to consume bits, the space for storing zeros as much as possible. So we just ignore the zeros which come between the buckets. So that is the first rule. What is the second rule? Every position with a 1 is in some bucket. So every 1 has to be in some bucket. So that is the second rule. So like you can have zeros which are not in the buckets, but you cannot have ones which are not in the buckets. Everyone has to belong to some bucket. So that is the second rule. No position is in more than one bucket. So that means there is no overlap. So that is obvious, right? We want to count the number of distinct number of ones. So obviously there should not be any overlap. So that is the third rule, which is quite intuitive. And there are 1 or 2 buckets of any given size up to some maximum size. So we don't allow more than 2 buckets for now. I mean, you can allow more than 2 buckets, but it has some downsides, right? One downside is that we talked about it, right? The storage, there's a storage cost also for the buckets. Then the fifth rule is all sizes must be a power of 2. So the number of ones contained in a bucket must be a size of 2. So that is important. Otherwise, counting will be difficult, right? We want an easy count to be maintained. So we want to count based on this sum. So if it is a 2 power, if it's a power of 2, then the counting would be very easy. And buckets cannot decrease in size as we move to the left. So as we move back in time, the buckets should only increase. They cannot increase, they cannot decrease. So those are the 6 rules. Now let us take an example and see, did we miss anything? And in general, if you forget the algorithm, one key statement that helps you remember is, so for every size of the bucket, we can have at most two buckets. And the sizes should be power of 2s. And the newest bucket forms on the right. So these are the 3 aspects of the algorithm which will help you remember the pseudocode, right? That's it. So these rules kind of ensure the order and predictability. So that is crucial for correctness. So let us take an example and see uh, how this algorithm works. So, so here's a hands-on example. So each time a one arrives, we create a new bucket of size one, right? What is a bucket in the algorithm? The bucket is basically a record, right? The record comprises of two uh, items. The first is the number of ones between its uh, beginning and the end. So this is the first item in the bucket. So it is a number of ones between its beginning and the end. And the second is the timestamp of its end. So this is the timestamp. See, the timestamp is 3 here. Step 3 is timestamp 3. So we save 3 here. So we just need logarithm of n bits for storing this value. And for storing the timestamp itself, we need logarithm of n. So a number of algorithms are based on this algorithm. So there's one popular algorithm called hyperlog. So you now know why that log comes in the name, because we need just the logarithm of the number of bits to store the number of the count of ones in the bucket. So that's where the log comes in. So logarithm of logarithm is much less than log squared, right? So this is a much efficient algorithm than the intuition that we covered earlier. Okay, let us look at the example now. So, so this is a stream 10110111. So the first bit that we encounter is a 1. So we are going left to right. So we get 1 here, and this is the time step 1. So we create a bucket of size 1. So we write the bucket as 1 comma 1. Now in time step 2, we get 0. So we ignore 0. We don't even store it. We don't do anything. Now third bit is a 1, right? So now there is a second bucket with the same number of ones, the same size. So the first bucket was containing a single 1, and the time step was 1. And now a second bucket was started with a count of 1 and the timestamp as 3. Now in the fourth time step, again we get a 1. So because we cannot have more than 2 buckets of the same size, we merge the oldest 2 buckets. Uh, so this so we merge the buckets to get 2 ones in one bucket with the timestamp 4, and just 1 bit set with the timestamp at 3, right? So we merge the buckets of the same size. In the fifth time step, we get a 0, we ignore. So we don't do anything, the buckets remain the same. Now the sixth, we get a 1. So we create a new bucket with timestamp 6 and count 1, so on and so forth, right? Whenever we get 3 buckets of the same size, we merge the 2 oldest ones into one of double size. So to combine any 2 adjacent buckets of the same size, replace them by 1 bucket of twice the size. So if you notice, the sizes are in multiple are in exponentials. Of course, the last bucket is still forming, so it will not be complete. But otherwise, the buckets are all of sizes to the powers of 2. Um, so one other thing that we need to do is that's how the buckets are growing and forming and all that. And also remember that the timestamp of the new bucket is the timestamp of the rightmost. That means the later in time of the two buckets, right? Uh, Now remember, this is a sliding window. So window means we need to maintain only a fixed number of bits. So what we do is we check the rightmost, that means the oldest bucket. And if its timestamp now has reached that current timestamp minus n, then this bucket no longer has any of its ones in the window. So we just drop it from the list of buckets. So you get the idea, right? So here the first time stamp is 3 and the newest timestamp is 8. That means we are storing 5 time steps. So if our limit is only 4 time steps, we drop this last bucket. Sorry, we drop this last bucket, right? So that is the other thing that we do. So as bits fall off the window older than n, delete the corresponding buckets. So that's what we do. So this process ripples through the bucket sizes. So once you drop, you need to ripple through the sizes. So that is pretty much the algorithm. A little bit involved, but not too involved. Now the error analysis. So what is the bound on the error? Remember, we need a bound on the error. We cannot accept algorithms which have an unbounded error. So what is the cost of all this approximation? So the good thing is that the DGIM algorithm guarantees that the error in the counting of ones is at most about 50%. So the upper bound on error is half, since the size of the last bucket cannot be more than 50% of n, since all are of sizes of powers of 2, right? So you get the idea, right? So the error is all in the last bucket, which is still forming. So, and that error cannot be um, more than 50% because we are counting 50%, and then uh, these are all powers of 2. So if you add up the powers of 2, it will be 2 power r minus 1, where 2 power r is the size of the last bucket. So if we allow k buckets of the same size, so here we allowed only 2 buckets of the same size, but if we allow k buckets of the same size, the size of the last bucket cannot be more than n by k, right? Even assuming that there are all the n bits are fitted into k buckets, they cannot be more than n by k buckets. So the error is bounded by the size of the last bucket, which is n by k. So that is like 1 by k times the total size, 1 by k percent of the total size, right? So that is the upper bound and the error. So in our case, we chose k to be 2. The number of buckets of the same size allowed is 2. So the error bound is 50%. So yeah, the downside of having more buckets of the same size is the storage, as each bucket stores timestamps and counts. So that is the problem. So we need to strike a balance between accuracy and storage, right? And once again, the error is all because of the last bucket. Otherwise, the remaining buckets, the count is pretty accurate. The error is coming from the last bucket, and the 50% n by 50 n by 2 is really the worst case, right? Typically, that is not the case. Uh, So that is the advantage. The upper bound is 50%, but typically it is much better. So that is the idea. So any questions? There are no questions so far. Okay, uh, so then let us move to the next topic, which is computing moments from data stream. So now we shift to a deeper statistical question, not just counts. What if we want more than counts? For example, we want to know the variance or skewness of the frequency distribution. So for that, we need to involve what are called as moments. So the concept is very similar to the physics moments. You would have all studied the moments in physics in the context of physics. So the concept of moments in statistics is not too different, but I'll not go into those details because this talk is about streams and not about um, not about the idea, the philosophy behind moments, but they are very similar to the physics moments. Um, so, so, so like the second moment tells you the sum of squares of frequencies, right? Um, uh, anyway, I'll cover the idea of moments in the next slide also, but again, the problem here is we can't store all the data. So we need to approximate the value of the moments using clever sampling. So the algorithm we are going to talk about is called AMS algorithm, named again after the inventors of the algorithm. So it is another landmark in the streaming theory. So roughly, right? Okay, let me explain what moments are in a very rough way. So moments of a function are certain quantitative measures related to the shape of the function. So what is the function here? It is the probability density function that we are referring to, or the frequency function, the frequency of items in the stream. So um, so if the function is a probability distribution, then the first moment is the expected value. The second moment is a central moment, is called the variance. The third moment is the skewness. It tells you how skewed the curve is, the probability density function is. And the fourth is called kurtosis. It tells you how tailed, it's like the measure of the tailedness of the probability density function. So it kind of tells you the shape of the probability density function. And probability density function, remember, is same as the frequency density function. Why? Because probability is estimated based on the frequencies. So the denominators are all same, the total number of items. So the numerators tell you the probability. So there's no difference between the shape of the probability density function and the frequency function. So, so it kind of tells you the shape of the frequencies of the items in the stream. So mathematically, the kth moment of a sequence of numbers is given by the frequency of an item. I is the item, m is its frequency in the stream, to the power k. So let us take an example. The stream is 2, 3, 1, 3, 5. So what is the frequency of the element 2? The first element is 2. What is the frequency of the element 2 in the stream? It occurs only once, so the frequency is 1. What is the frequency of 3? It occurs twice, so the frequency is 2. So similarly, number 3, sorry, 3 we already talked. So number 1, occurs only once, so its frequency is one. So you get the idea. You compute the frequencies. Now the zeroth moment is when you take these frequencies to the power zero. What does this represent? Any ideas? Anyone wants to guess? So it is the number of distinct elements. So the same thing that we considered in the previous algorithm, right? So the DGIM algorithm we talked about so far gives you the number of distinct elements, which is the zeroth moment. So we are already in the moments area. Even DJM is a way to compute the moments, the zeroth moment rather, not moments, but just the zeroth moment. So that is the zeroth moment. So what is the first moment? What does the first moment represent? It gives you the count of the number of elements. So the length of the stream, it's basically the length of the stream, which is easy to compute. What does the second moment tell you? It tells you how uneven the distribution is, right? Suppose the stream, there is a stream of length 100 and there are 11 distinct values. The 11 distinct values are, the first value is 10 and all the remaining values, the remaining 10 numbers are ninths. So what is the second moment? So it is 1 squared plus, sorry, 1 second, 1 squared plus 10 squared. No, there are 11 distinct values. 1 second, let me think. Um, so there are, okay, I think I'll take the example from Google because it is hard to explain in words. But you get the idea, right? I mean, in terms of normal statistics, the second moment it corresponds to variance. So the second moment is also called surprise number. So I will show this on Google. No, this is not what I mean. Second moment, surprise number. Yeah, so we square the frequencies like this. We sum the square, we get 59. So that is the surprise number, but it is not showing the surprise, unfortunately. Okay, let us look at the first link. Continue to this fine. Yeah, so this is an example, right? So, uh, so, so there are 11 values. One of them is 10 and the other are nines. So the surprise number is 910, right? Because you count the squares. Whereas if the frequencies, if the stream is 90 followed by 10 ones, then the surprise number is 8110. So it tells you how uniform the stream is. So here the stream is a lot more uniform than this stream because it's very jerky, right? So the first frequency is 90 and remaining numbers repeat just once. So this is very jerky. So the surprise number is 8110, whereas when the frequencies are more uniform, the uh, the surprise number is less. So that is the idea. That is what the second moment tells you. All right. So hope you got the intuition for the second moment. Now the third moment is raise these frequencies to the power 3 and so on and so forth. So that is the idea of moments. So but the challenge is you have to compute these moments from a stream, which makes it a problem. That is the problem, right? So these three inventors, Alon, Matthias, and Zajedi, so they came up with this ingenious way of computing the moments, not just the first moment or second moment, but for all the moments. But for now, for illustrating the algorithm, we will just concentrate on the second moment. So the idea is we have an input stream of length n, a1, a2, and so on. And the number of estimators, we keep track of a number of estimators, right? So, okay, we'll talk what estimator is and all that. So, so k is the number of estimators, right? And then we initialize. What is the initialization step? For j is equal to 1 to k, we choose randomly a timestamp in the stream. So, and keep track of the element at that timestamp. So we pick and keep track of a number of elements in the stream, right? And then we start counting the occurrences of that. So instead of, so typically what would we have done? We would have kept track of A1, A2, and so on and so forth, and then started counting the number of occurrences of A1, number of occurrences of A2, and so on. But this algorithm says that you don't have to keep track of each element. Just choose k number of elements from the stream randomly, and then keep track of the counts for only those elements. That's what it says. So the element itself is stored in xj.el, and the count, the number of times it occurred, is stored in the xj.val variable. So you process the entire stream like that. So for all the time steps uh, till n, we started with tj, time step j, because that's the first place where we started. So from tj to n, tj plus 1 to n, we keep counting the occurrences of the elements that we are keeping track of. So we keep incrementing the element counts. Now, so now how do we estimate the estimate the counts at the second moment? So this is the engineering part, right? So what the inventors say is that we compute this value. N is the total number of elements in the stream, and we multiply the count for each element that we are keeping track of by 2, subtract a 1 from it, and store it in the in a value called Sj. Sj kind of is indication of the second moment here. So we do this for all the elements that we have been keeping track of. So 2 times the count of that element minus 1 multiplied by n. And then the final output is the average of all those counts, right? You compute the average of these numbers, and that is the second moment, estimate for the second moment. So that is the interesting part. So for each element x, we store x.el and x.val. X.el corresponds to the item I, and val corresponds to the count of the item I. right? But so why are we doing this? Why are we not keeping track of every element? Because our memory is very limited. So the number of elements we are keeping track of, the k, also depends on the number of the storage that we have at our disposal, right? So here's an example. So this is the stream. So at timestamp 1 you got A, timestamp 2 you got B, so on and so forth, and there are 15 timestamps here. So there are 15 elements in the stream. The stream is this. The number of elements in the stream is 15. So A occurs 5 times. 1, 2, 3, 4, 5. So 5 times. B occurs 4 times. C occurs 3 times, and so on. So the second moment is given by 5 square plus 4 square plus 3 square plus this square, which is 59. Right? This is how you compute the moments. Now, according to the AMS algorithm, we don't want to keep track of each and every element. We just keep track of the elements at positions. We have to determine the positions, but we want to keep track of just 3 variables. 3 timestamps we randomly choose and keep track of the elements there. So at random, we pick the 3rd, 8th, and 13th timestamps positions to define these 3 variables. So what does that mean? X1 dot element is equal to C. So at position 3, C is there. At position 8, this is randomly chosen. Um, D is there. And at position 13, A is there, right? So these are the 3 elements we are going to keep track of. So we start with position 3. So remember, the loop in the algorithm starts at tj plus 1, the first item picked randomly. So we start with 3 at position 3, and we set x1 dot element is equal to C and x1 dot value is equal to 1. Now we start with the position 4. It holds B. So we don't change x1. Why? Because we don't care for B. We are only tracking C here. We don't care for B. So similarly, 5 and 6 have D and A. We are not tracking D or A. We are only tracking C as of now, right? So we just ignore those positions. Now at 7, we see C again. So we set x1 dot value to 2, right? So we continue doing this. So at position 8, our chosen position, we get element D and we set the count to 1. 9 and 10 do not contain either C or D, which we are keeping track of, so we just ignore. So 11 holds D, so we set x2 dot value is equal to 2. So 12, x1 dot value is equal to 3, because we are keeping track of C, so we increment the value, the count of C, and so on and so forth. We keep doing this until the stream is exhausted. At the end of the 15th element, we see that x1 dot count is equal to 3, x2's count is 2, x3's count is also 2. So now the estimate for the second moment, based on the values we observed, for the first x1, it is 2 x1 dot value minus 1, which is the value is 3. We observed 3 x1s, 3 x1 value elements. So 2 into 3 minus 1 multiplied by 15, which is 17. So that is the estimate. Based on the first element, the estimate of the second moment is 75. Based on the second and third element, because the frequency is the same, the counts are the same, we can estimate them in a single shot. So for both, the estimate is 15 times 2 into 2 minus 1, which is 45. So for the final estimate, we take the average of all the 3 values. So which is 55. You can 75 plus 90 divided by 3 is 55. You can count that. You can calculate that. So the true value was 59, and the average of the three estimates is 55. So it is pretty close. So the estimate is not too bad, right? So this is the power of randomized algorithms in streaming. You get statistical truth from partial views, right? Sketches. So I talked about sketches in the other video. So even though we tracked just 3 samples, the result closely matches the true moment, which is 59 in this example. So that is the power of the algorithm. So why does it work? So the question is, I mean, the algorithm itself is simple, but why does this algorithm work? So for that, we need to understand, we need to get some intuition, right? So remember that each sampled element represents all others like it, but it has to be weighted by probability. So the chance that we sampled any particular element is what? Each element has equal chance of getting sampled. So the chance is 1 by n. So its contribution to the estimate is unbiased. So by squaring the counts, we capture not just frequency, but how unevenly items are distributed. So this is essential for detecting the skew. Anyway, let us take a more simplistic view of the intuition. So what is the sum of the first m natural numbers? It is m into m plus 1 by 2. And what is the sum of the first m odd natural numbers? It is simply m squared. From m into m plus 1 by 2, you remove the even numbers, you get m squared, right? And what is the expectation of a roll of dice? So if you remember the roll of dice, this is a problem from probably high school math or middle school math. So you multiply the face value of the dice with the probability, which is 1 by 6 of the face, you get the expectation. So these three concepts you need for understanding why this algorithm works. So this theoretical grounding will give you confidence that this algorithm will work. So these things you need to know. Why is it not advancing? My slide is not advancing. Okay. So, so now that is the intuition. Let us apply to our problem itself. So what is the expectation of this second moment, which is given by n into 2ca minus 1 for any element a? Any guesses? So here we reason through expectations, right? So we want to compute the expectation of the frequency squared, which is the second moment. So it turns out that it matches the contribution of its element to the true moment. So this element Ca, it it kind of matches the expectation matches the contribution to the of this element Ca to the true moment. So that's the reason why we are wondering what the expectation is. So to calculate the expectation, we assume that the element occurs at every position. It obviously does not occur at every position, but it occurs at every position with a chance. There is a chance that the element can occur at pretty much every position, but the chance is given by 1 by n, right? So the probability that the element occurs at any position I is 1 by n, because we did not make any assumption about the stream itself. So each the element can appear in any position uniformly. So it is 1 by n, right? Not uniformly, sorry. With equal probability. I should not use the word uniform here. With equal probability. So, the value of SA at various positions. So what is the value of what is the value of CA at position 1? So at position 1, the value of CA will be 1, right? Because that means it has occurred only once. If the same element A has occurred twice in the second position also, then the value of CA will be 2. If the element A occurs in the third position also, the value is 3, so on and so forth, right? So we can easily prove that the expectation of SA, this term n into CA minus 1, will be equal to the second moment, right? So even though we sample, the law of expectation fills in what we did not see. That is the beauty of math. So unbiased estimation through random sampling. So if this is a bit hazy for you, let us take an example and say the same thing, same intuition, but using an example. So we consider the same stream. So what is the probability of x1 dot element is equal to C appearing at the fourth, fifth positions? What is the probability? It has the same probability. So it has occurred at the position 3. And what is the probability that C will occur in the position 4 also, and 5 also, and 6 also? It is just 1 by 15, right? 1 by n, because it has equal chance of appearing. That is the reason why the distribution is not uniform, because every element has equal chance and it is sporadic. The elements can occur sporadically. So what is x1 dot value at the fourth, fifth, and other positions if C appears in those positions? If it appears in the fourth position, what is the value of CA? If it appeared in the fourth position, it means it has occurred twice. That means the value of CA, which measures the frequency, is 2. If it occurs in the fifth position, it is 3. Sixth position, it is 4, so on and so forth. So the reason is because it is repeated twice, thrice, and up to its actual count. So we will use this to compute the expected value of the second moment. So what is the expectation of the second moment using x1 dot value alone? You have to multiply the value with its probability. So 1 by n times the formula. So 2CA minus 1. So for the position 4, for the position 3, the value of CA is 1. Position 4, the value of CA is 2. Position 5, the value of CA is 3, so on and so forth. But each one of these occurs with a probability of 1 by n. That's why we multiply with 1 by n. And of course, n was always there before. So we end up in 1 by n times sum of the first n odd numbers. So if the same element occurs in every location in the stream, the moment will be n squared, right? So you see how it works? So the above is applicable if x1 dot element repeats in all n locations, but that is not the case. We therefore sample multiple unique elements at random. The expected value of the moment for each x dot value is equal to sum of first mj odd numbers, where mj is the count of the respective x dot element. So remember, if we do this process for every unique element, we get the exact moment. But we rarely sample all unique elements because we don't have the storage. So to reduce the variance, we sample multiple unique elements. Each one contributes an independent estimate. So averaging these reduces noise and improves accuracy. So this is how randomness becomes reliability in large data analysis, right? Simple intuition, right? Uh, so CA is the count, A is the element, SA is the estimate based on the element A for the second moment. And we proved that the expectation of SA kind of approaches the true expectation, right? So that is what we kind of used. So quite ingenious. So, so we only talked about the second moment. How about higher order moments? How about the third moment, fourth moment, and so on? So once you get the logic for the second moment, extending to higher order is quite natural. So these higher moments help identify patterns like the skewness of the distribution, the kurtosis, or even outliers, right? So this is important in anomaly detection and other applications. So, so the interesting thing is the same sampling and expectation trick scales up very nicely. So for a randomly chosen time t and corresponding item j is equal to at, let C be the number of times j appears from time t onwards. To estimate the kth, I mean, just like before, right? The same idea. We don't sample all the elements. We sample only a few elements. To estimate the kth moment, uh, we approximate the kth moment with this formula. So that's quite interesting, right? So why is that the case? We'll see in a bit. But for each randomly chosen element, we do this. And then like before, we take the average for all the elements. So why does this work? Let us apply the formula for k is equal to 2. So k is equal to 2 is c squared minus c minus 1 squared, which is n into 2c minus 1. For k is equal to 3, same thing, and so on. So you can probably use mathematical induction to prove that this actually holds. So we divide the stream into groups, apply the AMS to each, and take the median of the estimates from each group. So that is how typically the moments are calculated. So the AMS algorithm pretty much gives a whole toolkit for understanding the shape of data distributions in streams. So there are no questions. So let's go ahead with the new problem. So this problem is that we are given a stream and we want to find out which items appear more often than more than S times in the window. Again, we are concerned only with the window, and we want to find out which ones appear more often. So the solution to this problem, we could just count like we did before, and the naive way is to just count every occurrence. But that doesn't handle fads, spam, and so on. So trends, I mean, remember we are talking about trends here. So like Twitter trends. So if you have opened Twitter anytime, you would have seen these kinds of trends, right? Uh, Let me open my Twitter. I mean, you must all be knowing this. I don't have to. So what's happening? So these are the trending hashtags. So not all hashtags are shown. Anyway, it's showing the previously it used to show hashtags uh, like senator. So typically, yeah, see here. Yeah, previously it used to show hashtags, but looks like now it is looking at words. Either ways, so what it seems to be doing is instead of looking at hashtags, it is trying to identify the important words in a tweet and trying to identify trends in the stream of the keywords, right? Uh, so trends can have fads, right? Some trends just go up and go down immediately. We are not interested in those kind of things. We want trends which last a long time, obviously, right? We are not interested in fads. And there could be spam also. A lot of people might artificially, or even robots for that matter, might be artificially pumping tweets to boost discussion about some topics. So that is all spam. So we don't want those kind of keywords to be identified by Twitter, right? So our goal is to count with recency and waiting, right? So the newer events matter more, so they should get better weight. So this sets the stage for algorithms like exponentially decaying windows, right? So the problem is highlighting genuine trending hashtags. So it could be hashtags, but looks like Twitter has changed its algorithm to choose keywords uh, based on other factors, not just the hashtags that the users give, right? But we, for understanding the algorithm, we'll take the example of hashtags. So let us take a concrete example of Twitter style hashtags. So the idea is to count the occurrences of each hashtag, but skip spam, fad, spikes, and so on and so forth. And the other thing we need to take care of is that the newer hashtags must rank higher than the older ones. And the third is weightage should not only depend on count, but also time. So we'll give higher weight to recent occurrences and let the old ones fade away. So this models the social momentum. So things stay hot only if they keep being mentioned. If they are not mentioned in the tweet, in the recent tweets, then they fade away. So that's how the algorithm seems to work. So let us look at samples hashtag stream. So on the day that I checked Twitter long back, I observed these hashtags being used the most, right? So we see a long list of hashtags like dream big, glow up, no limits, and so on and so forth. So this slide illustrates how repetitive mentions can inflate apparent popularity, right? But we cannot just count raw frequency. We must also give more importance uh, to the time when they occurred, when the mentions occurred. So this motivates the exponential decay model that discounts older counts. We want to compute a smooth aggregation over the whole stream. So there are other websites also that update frequently and show what is hot across platforms. So LinkedIn is also like that, right? LinkedIn highlights the most important posts. It checks for the news in the posts and pulls up the posts and also the news which are trending. In fact, these trends are one of my primary source for news and opinions. I look at the trending news on LinkedIn and Twitter to get news. The reason is because these are opinions. I mean, if I look at, say, Wall Street Journal or New York Times, the reporters are not allowed to express their opinions. Whereas on LinkedIn and Twitter, we get the opinions as well, and the latest opinions, right? So that's the reason why I pay a lot of attention to trending hashtags, and that is the reason why I chose this algorithm to for today's talk. So exponentially decaying windows. So imagine the idea is we imagine each event having a half-life. Its influence fades exponentially over time. So we can mathematically multiply older weights by some term, so called the decaying factor, so that the recent data dominates the trend score. So EDW, as it is called, exponentially decaying windows, provides a real-time sense of momentum. What's currently hot, uh, and not what was hot last week. So the weight distribution, the recent items get higher weight, older items get exponentially decreasing weight, and ancient items almost get zero weight, so that they disappear from the list. So so traditional way of doing this is count the last n elements and compute a raw frequency score and use a fixed window size. This is the traditional way, but this does not take care of fads, spam, and all that stuff. So the exponential decaying window takes care of that. So there is a weighted sum over entire stream for each keyword identified, and that sum is computed using this formula. C is the decaying factor. Typically, it's in the range of 10 power minus 5 or 10 power, whatever numbers you are seeing on the screen. And so this kind of controls the decay rate. So what does this expression remind you? Does anyone recollect seeing this kind of expression? So this expression makes sure that the recent items weigh more heavily, right? So this kind of expression is typically used in depreciation calculation. In economics, finance, you depreciate some value, like house property. The property value depreciates every year, right, for income tax purposes and things like that. So this is the formula used for depreciation. So we use similar kind of formula here. So when a new item arrives, the update rule, multiply the current sum by 1 minus c and add the new item uh, to the weight. So new sum is 1 minus c times the old sum plus there's a weight given, typically 1. So the weight is, so I mean, mathematically it can be expressed like this. So each time you multiply by 1 minus c, if there are t time steps, you will multiply 1 minus c, t minus I time steps, plus there is a initial weight. So this initial weight is 1 if the element occurs in that position and 0 otherwise. So what are the benefits of doing this? It's a smooth aggregation of all the trending words. There is no arbitrary cutoff, and we gradually forget old data, which we want, right? We don't want to read 1 week old news. We want to read the latest news. And then efficient incremental updates. So these are the benefits. So let us take a specific example, microblog trends. A microblog here could be Twitter, or could be some other microblog also. So consider a sequence of hashtags below. So these are the sequences. These are really the sequences of this is really the sequence of hashtags on Twitter when I searched. Any guesses when I searched these to get these hashtags? Which day of the week did I search? So this was a different day, and the previous one was on a different day. So this was on a Thursday. How can you tell? TBT stands for Throwback Thursday. So a lot of folks tweeted on that day with a hash TBT. So this is a sequence of hashtags that were trending on that day. So we want to find the most trending hashtag, right? Which hashtag do you think is more trending? So for that, we apply the EDW algorithm. So consider a sequence of hashtags below, like before, crypto, TBT, and so on and so forth. So even though both appear equally often, we will find that one hashtag is more trending because its mentions happen later. And that is exactly what we want also, right? We want a notion of freshness baked into counting. So it's a neat demonstration that not all frequencies are equal. And that way you can take care of spikes and spams also. Fads, spikes, and spams. New element is given more weight by this mechanism so that you get the right training output, right? So that is the idea. So let us look at the algorithm itself. So let each element's weight be 1, and C is typically 10 power minus 6. It's an exponent. It's a really small fraction, but if I use that many zeros, my slide will fill up very quickly. So that's the reason why I use 0.1. This is not the normal case. This is just for illustrating the example. So each element's weight is 1 to start with, and the decay is 0.1. So what is the aggregate sum for crypto? So first first hashtag is hash crypto. So an initial weight is 1. So we multiply 1 with 1 minus 0.1, which is 0.9. Next hashtag is TBT. So again, we multiply the previous weight with, so this is, remember, we are computing the aggregated weight for hashtag crypto. Whichever hashtag has the most weight will win eventually. So this is the sum for only hash crypto. But we got hash TBT. But still, because the time has lapsed, we depreciate the importance of crypto by using the depreciation factor 1 minus C. But this time, the weight of the hashtag is 0 for crypto. Why? Because the hashtag is TBT and it's not crypto. So it does not matter much to the value of crypto. So it's 0. So the weight now is 0.81. Similarly, the next token is hash crypto again. So this time the weight will be 1. We continue to multiply by 1 minus 0.1, but this time we add a 1 because we saw a crypto in the hashtag. So if you see crypto in the hashtag, it is +1. If you don't see it, it's 0. So the next one is hash TBT. That's the reason why the weight is, the additional weight is 0. And so on and so forth. We keep doing this. And we get the weight for crypto as 2.9215. By the way, you can guess which one is going to win, right? And see if that really, that's how you, if EDW matches with your intuition. So now the aggregate sum for hash TBT is has to be computed. So the first token is crypto. So its weight will be 0. So 0 times 1 minus 0.1 is 0. Then the next hashtag is hash TBT. So the weight is still multiplied by the previous weight. The depreciation factor is still multiplied by the previous weight, which is 0. But this time the weight, because hash TBT occurred, the additional weight is plus 1. So you get 1. Next is crypto. Deprecate the weight, but add a 0, um, because the hashtag is not TBT, and so on and so forth. So eventually we get a score of 2.72 for hash TBT and 2.92 for hash crypto. So hash crypto wins, right? So we can keep a threshold to ignore elements of weight lesser than that. So suppose if the weight is less than say 0.5 or something, we just drop that trending word, right? Because we want to capture the most important words. Here there are only 2 hashtags, but typically there could be many hashtags. So we don't want to keep track of trending hashtags if their weight goes below some threshold. So you can think of this algorithm as a memory with fading influence. So you can think of it as a forgetful counter, right? So crypto is more trending than hash TBT, though both occurred the same number of times. So one interesting question to answer is, I mean, because we are talking about weights and keeping only the the trends with certain weight in our list, the question would be, what is the sum of over all the weights? So on a first thought, we tend to think that the total weight of an infinite series cannot be a constant, right? But remember, this infinite series is geometric. So it's an infinite geometric series, which can be approximated by a formula. The formula is this. So you can look up Google, get more of the, oh man, it's showing ads. All these gimmicks, I don't know how to. Anyway, let me open it again. So yeah, an infinite geometric series converges if and only if the absolute value of its common ratio R is less than 1. If it is greater than 1, it does not converge. Fortunately for us, C is less than 1, right? So that's why it converges to this A by 1 minus R, right? So that is what we take advantage of, right? So here A is equal to 1 and A is the initial value. So A is equal to 1 and R is 1 minus C. So when you substitute these values, you get the geometric series converges to 1 by C. The sum of all these terms is 1 by C, right? So in exponential decay, older weights shrink indefinitely. So the total converges to 1 by C. So understanding this helps normalize or compare trends across streams. So what does it mean? It means that C kind of sets an upper bound on the number of items with a specified range of weights. That means C needs to be set appropriately. So it's a reminder to us. It's a hyperparameter. It's a tunable hyperparameter. So, so decaying windows require careful calibration of C to balance memory and responsiveness. So the reason is we do not want to record values for unpopular items. So you see LinkedIn. LinkedIn's value might go down if it flags in the LinkedIn posts, right? Um, so yeah, I think LinkedIn is a better example than Twitter. So even in LinkedIn, right? See these LinkedIn news, how are they captured? So it is based on the posts, perspectives expressed, right? The most trending perspectives are captured. So they must be looking at the keywords and computing the weights for the keywords and doing something very similar to what we are talking here, right? So that's what I'm referring to. So if they flag old news and not trending news, the readership will go down drastically, right? So many people, at least I access LinkedIn. One of the main reasons I access LinkedIn is for the news. So if they show news that is spam or fad and things like that, the value will go down. So they must be using something like this, what we talked here in this algorithm. So now we go beyond single items to item sets. So that means not just single hashtags, but combinations of keywords, combinations of item sets. For instance, you take market baskets, like in a store. So we want to look at item sets like bread and milk. So somebody who buys bread typically buys milk also, right? So we look for those kind of combination in market basket data. But so there are for non-streaming data, there are other algorithms. Um, so if you have observed, the streaming algorithms are simpler than their non-streaming versions, right? But only thing is their intuition and their proofs are difficult in streaming, right? Otherwise, the algorithms themselves are simple. Why are they simple? They have to be simple because of computational complexity uh, considerations. If they are too complex, then it will take a lot of time, and stream requires velocity, right? This is the second V of big data, velocity. First V is volume, second V is velocity. So what is the challenge here? So the challenge is a combinatorial explosion. So the number of possible item sets grows exponentially, and that also in a stream. So we need smart pruning and assumptions to track only promising item sets. So this connects streaming analytics to classical data mining concepts like association rules. So in the non-streaming setting, we studied these similar algorithms in the topic of association rules. So we follow a similar kind of approach, but with some with some changes. So just to refresh your memory or your knowledge, what are item sets? So if the items in the market basket are bread, milk, eggs, and so on and so forth, the single item sets could be bread, milk, eggs. Item sets could be bread, milk, all the combinations of two item sets. So you see why it's exponential growth, right? Because of the permutations involved. So for item sets, we obviously need to distinguish between baskets. So no longer just a single stream of bits. So item sets are groups of items bought or observed together, right, in the same market basket. So singletons, pairs, triples, so on and so forth. So each level adds a complexity, right? The data stream might represent shopping baskets, sensor events, or user actions. So why do you want to understand, why do you want to analyze item sets? It helps in understanding uh, how the buying patterns of people, right? The co-occurrence patterns in real time, right? But the problem is combinatorial explosion of item sets. So the number of possible permutations of sets of items grows incredibly rapidly as the number of items increases, right? So for instance, so the idea is keeping track of new item sets in addition to the items. So single item sets. For that, we start the count of a new item set only if all its subsets were being counted before, right? So we need some ways to control the explosion, right? Okay, I'll give you an example of an explosion, right? Uh, so if there were 20 items in the store, and if we counted every set we saw, uh, so uh, one market basket of all the 20 items in the store would initiate 2 power 20 um, possible item sets. So that is 1 million. 2 power 20 is 10 power 3 into 10 power 3, which is 1 million. So roughly 1 million counts are initiated if you just have 20 items in the basket. So that is what we are looking at. So the key insight here is to track only the larger item set if all their subsets were also occurring frequently. So that's what we do. So start the count for a new item set only if all its subsets were being counted before. So start count for A comma B comma C only if all the possible subsets were counted before. So that is an additional consideration to control the explosion. So this filters out unpromising combinations early. So it will dramatically cut computation costs. So, um, so the assumption is if the subsets weren't popular before, the item set wouldn't be either. That is the assumption. And we apply one more criterion to reduce the explosion. So we drop any item set whose weighted frequency falls below a threshold. For instance, if the weighted frequency falls below 0.5, we just drop it. So that keeps the summary lean. So this is how streaming association mining stays feasible. So guided and incremental counting. So that's all. We make these small changes to the algorithm, EDW algorithm, and we are good uh, with counting item sets. So that pretty much covers the talk for today. So we have traveled from bit counting to trending hashtags, but all of them under the same philosophy. We need to approximate to survive in data streams. So real-time analytics is all about agility, not perfection. So same thing with your time management, right? If you want um, if you want to accomplish a lot of things, maybe you have to sacrifice a bit of perfection, right? For instance, I could have probably done a better job if I rehearsed or if I even went through the slides once thoroughly. But I did not have time to do that. Uh, but it is what it is, right? So same thing with real-time analytics on big data. So, the algorithms that we covered today, Flajolet-Martin at a very high level, DGIM, AMS, EW, these are EDW. So these are backbones of modern stream processing. So So the question still remains open. How can we continue to design new summaries that capture what matters in a particular domain? For machine learning, for instance, the summary is a model. The data on which a machine learning model is summarized is called a model. It's a set of weights. So for each domain, we have a different way to summarize. So in EDW, we did it in one way. In DGIM, we did it in another way. AMS, we did it in a different way. So the goal, I mean, the idea is to stay curious and of course stay connected to exchange these kind of ideas. So that's how data stays alive. So any questions? It has been a quiet gathering today, surprisingly.
Yeah, I'll just say one thing. A lot of this is new to me. I'm a software developer and not a mathematician, not a data scientist. I just want to thank you for introducing me to so much stuff. It was great. Thanks.
Thank you. Thanks for the feedback. All right, looks like there's nothing else, so I will close the uh, call and hope to see some of you at least in the next future events as well. Thank you all.
Yep. Thanks a lot. Good night.